Hello, statics class. This is equilibrium analysis problem number 4. It is still February the 12th, and this is continuing our virtual lecture of the day because Skagit Valley Community College is closed today. Okay, so we have in this problem, here's our given. We have two rods. We have them pinned together. They're both supported at by pin connection. So A is one pin point, and B is another, and then there's a pin connecting rod A to basically rod BC, this long one here. And we have a force, FA, being applied vertically downwards on rod AC, and then we have a force B yanking horizontally and to the right at the very end of rod BC here. So the magnitude of force A is 500 pounds and the magnitude of force B is 1,000 pounds. And the question asks us to find the forces at the three pin connections. So that's the two support reactions, and then what's the force going through the pin between them. So just looking ahead, this is the kind of thinking that we'll need when we analyze, again, trusses and frames. And obviously, if you're making any kind of machine where you might be choosing a bearing or a pin, these are the loads that you would be directly applying to those shafts, and that would be the input for, say, a fracture analysis or something else. Pin connectors tend to be very rigid, tend to be fairly strong, and so they can be fracture critical items. So understanding the applied forces is really important. So here we go. One of the most common and simplest ways to approach these types of problems, and it's kind of my go-to default. At worst, it gives me a couple of forces that I may or may not be able to use, but I like to start with a whole body FBD. I forget about all the internal structure. I kind of, in my mind, pretend it's welded together, and then I simply look at the forces that are being applied external to that body. Once I've established that, then I start cutting it up on the inside and looking at the nature of the internal connections and force transfer capabilities. But to start with, I just assume that the entire body is a blob. I recover the geometry that I need for the relationship of the external forces, and then just pretty much try to solve for the support reactions. And that tends to lead to the quickest and simplest solutions. So here's my whole body FBD, and to remind myself, again, this is a trick that I use. You don't have to use it if it doesn't work for you, but I actually deliberately draw the body as a big blob, and that's to remind myself that I'm not going to sweat how it's connected together. I'm not going to think about this pin in the middle. It doesn't exist. It's a blob. I do need to know where the support reactions and the applied external forces are being applied, and I need to know their magnitudes. So I'm going to need to know the distance between A and B, and I'm going to need to know the application point of force A and force B relative to the support reactions, and I'm going to need to remember the nature of the support reactions, like they're pins, so they have components acting vertically and horizontally. They cannot apply moments. So there I go. There's my FBD, and I don't have the distances drawn on these, but we can look up here and take them. So the distance between A and B, it's only horizontal. They're in a line. That's 8.485 feet, and I've done some geometry to harvest off the application point for force A and force B. And so when I throw those into equations of equilibrium for the whole body FBD, I can use sum of the forces in the X right here to say 1,000 pounds, which is FB, acting in the positive X direction, is going to plus BX, my B support, which I've drawn in the positive X direction, minus, AX, my X component of my A support reaction, which I've drawn default in the negative X direction. That has to equal 0. Sum of the forces in the Y. I have both of the support reactions acting upwards. They are opposed only by FA, which was 500 pounds in the downward. So let's see, 1, 2, 3, 4. Got 4 variables and 2 equations, so that's not enough. Let's see if we can get something out of our moment equation that will isolate one variable totally. If we can't, we won't sweat it, because we may be able to get it from one of the other FBDs, but if we can get both the support reactions, that would be really nice. So we're going to take the sum of the moments around, in this case I took it around point B, and again that's because I have 2 unknowns concurrent at point B, B sub y and B sub x forces, and so if I take the sum of the moments around point B, those 2 go away, and I only have AX and AY to contend with. And lucky me, because A and B are on a horizontal plane, AX is also concurrent with point B, so its line of action goes through point B. So really, I only have one unknown force that is going to enter into the sum of the moments equation around point B. So that was a slam dunk. So I can just write it with its geometry. Again, using the right-hand rule, it's going to end up creating a negative moment, my AY. It's acting at that horizontal offset distance of 8.485 feet, and it's opposed by my FA of 500 pounds with its distance and direction offset, and then again my other known force of 1,000 pounds with its geometry for the moment. So out of this equation, I get AY of 1,208 pounds. I can plug that back up into my sum of the forces in the y equation and get BY. Now this did not give me AX and BX. Unfortunately, I had 3 equations total and 4 variables. So I can get BX in relationship to AX, but I don't know them explicitly. And unfortunately, that was part of what was asked for in the problem. But I have the y components, which is very important, and a relationship for the x components. So to go any further now, I'm going to have to start cutting that body up and looking at its members individually. Okay, so we are back to our 2 pinned bars in our equilibrium analysis. I believe this is our example number 4. And we had just finished the whole body FBD, where we solved for the y components of our A and B support reactions, but we couldn't get the x components explicitly in numbers because we had four variables and only 3 equations. So now we're going to delve into that body, and we're going to separate the given members, and we're going to draw FBDs on them, and we're going to get a little bit more information by applying equations of equilibrium separately to different members. So we're going to start with the longer force, or excuse me, the longer rod, BC. So this is the BC rod's free body diagram. So up at the top here we have our B support reaction, and we have a downward force there of 708 pounds, and again that came from our whole body FBD. We have the BX support force that we couldn't solve for, but we know it's there. We have our applied force of 1,000 pounds that came from the given, and then we have the forces in the y direction and the x direction of pin C, which is connecting this rod to the rod AC coming in from the side, which we're not showing. We're merely representing its effect by forces of pin C on rod BC. And so we chose arbitrarily that pin C would exert a force upwards and to the left on the rod. So of course, if we were to ever need to isolate the pin, we would represent the force of the rod on it downwards and to the right. So action, reaction. And it's really important to keep your signs straight when you're cutting up these free body diagrams, especially when you look at pin supports. So if a pin is pushing up on something, the bearing that that pin is sitting in is going to push down on the pin. So That's a one way to really make mistakes, is to get your signs wrong and ending up with doubling forces. And luckily, we will end up with a redundant set of equations for this, so we can check for those mistakes really easily and go back and find them. But it's better not to make in the first place. So we can write equations of equilibrium. We have a free body diagram. Let's put it to use. So let's start with the x direction. We have 1,000 pounds in the positive x, we have bx in the positive x, and we have cx in the negative x. So let's go back and check and see if how much we're gonna drop out of this. We have 1, 2, 3 equations, or excuse me, 3 variables, and we know that it's two-dimensional. We should have three equilibrium equations, so we should be able to solve for all 3 of these. It may not be easy, but we should be able to get them. We have 3 equations and 3 unknowns. So looking at the y direction, we're going to be able to get cy directly, because only cy and the 708 pounds of downward force coming from our B support are in the y direction. So cy is equal to 708 pounds, and that is in the upward, the j hat direction. So the pin is pulling up on this bar. So we can then use a moment equation to hopefully get bx and cx now that we know cy. So it looks like we took the moment around point B, and we used what we knew about cy and the fact that we can now solve just directly for cx. So that's what we did. So this moment expression is the sum of the moments about point B up here. So here's the moment about point B due to cy. Here's the moment about point B due to cx. And here's the moment about point B due to our 1,000-pound force out at the end of the rod. That gives us cx of 958 pounds positive for the direction shown on the free body diagram. That's why it says in the direction shown. Highly recommended that you annotate your problem, that you give clear indication of what direction things are. If you need to note this is the force of the pin on the rod or the rod on the pin, go ahead and write that down to keep it straight, because if you make a mistake and you're going back to find it, you have your assumptions right there, and if you got it wrong, then it's obvious, you correct it and you're up and running. Otherwise you might have to start all over again, waste a lot of time. So we know that the pin is pushing upwards and to the left. The direction that we presumed on the FBD turned out to actually be the way it's going. So knowing Cx, we can plug back into our sum of the forces in the x equilibrium expression and get Bx, and it's pointing a negative 42 pounds in the direction shown. So it's actually pointing back to the left as well. So it's pointing opposite the direction presumed in the free body diagram. So we now have complete support reactions of B, and that was one of the questions that we needed to know to answer one of the finds, excuse me. What was asked for in the question was, what are the forces at pins A, B, and C? So we now know the forces at pin B. It's negative 42 pounds in the I direction and negative 780 pounds in the J direction. So quite a bit of Y force in the downward direction. So we can plug those values back into our whole body FBD, which we already solved for that are on the previous page, and solve for AX. Remember, we had AX in terms of BX, but we couldn't solve for each one explicitly. Well, now that we know BX from our BC rod FBD, we can go back to our whole body FBD and get AX. So the only thing that actually does give us everything. Now that I think about it, we now have pin A, which is, we'd have to refer to the directions back to the whole body FBD. but it looks like it's pulling upwards with 1,208 pounds in the vertical, pulling upwards. And I believe that it was negative presumed direction, so it's probably pushing to the right. But again, go back and check the FBD to see what the direction was. This should be reference to one coordinate system. Okay, this is the last portion of our equilibrium analysis problem, example problem number 4. And as I had mentioned, that we should have a redundant FBD coming out of this problem. And actually we have 2 if we want to isolate the pin at C. We can actually do a check to make sure we didn't make a mistake, sign error or some other problem in solving the problem by plugging in all of our directions and force magnitudes and then making sure that the remaining bodies are actually in static equilibrium. And that's what we've done here with our free body diagram of our other rod, our rod AC. I plugged in the values for our support reaction at A, which were indeed pointing upwards and in the negative J direction, just as indicated here. And then the 500 pounds downward, the given FA, and then what we had determined the reactions at pin C to be, and do they all add up? Yes, they do. So that's a good thing. So that was a check. We can be sure that we did our math right, made our assumptions right. We can likewise look at pin C, and we can look at all of the forces coming from the rods on pin C. So there's going to be 4. We have rod AC. It can exert a force in the Y and the X direction on pin C, and we have rod BC, which can likewise exert forces. So this is our second check, our FBD of pin C. So we actually were lucky we had 2 checks and they both checked out. So again, steps to this problem: start with a whole body FBD to isolate your support reactions as much as possible. We got 3 out of 4 this time. Then start cutting up your members and getting your other reactions just based on some of the forces, some of the moments, and keep going until you have all the ones you need. Generally, you will have 1 FBD remaining if you start with a whole body FBD, which you can use as a check. If nature gives you those extra conditions of equilibrium, an extra FBD to use as a check, always do that. I can tell you it's the only sure way of making sure that you didn't make a mistake in most cases. Sometimes you can just get it from gauging order of magnitude. Does this make sense? But in other cases, your geometry is going to be so complex that there's really no way of intuitively seeing if something's going to be in compression or tension or what the magnitudes of forces are going to be. That's one of the reasons we learn statics and we do these types of analyses, because it's quite often totally opposite what you'd think. But if you have a spare set of equations and you plug into them and they don't check, that's a sure sign that you made a mistake. So always take advantage of those. Anyway, so that is it for our 4th example, and I believe we have a couple more today to help you with your studies, and we'll get back to that.